Question 1. When evaluating a situation where a commercial pilot is experiencing significant fatigue symptoms, including reduced concentration and slower reaction times, prior to a scheduled flight, which approach best upholds regulatory requirements and professional ethics concerning pilot decision-making and risk management? Option A. Proceed with the flight after a brief self-assessment, believing that experience will compensate for the fatigue, and inform the dispatcher of the symptoms. Option B. Rely on the dispatcher to determine if the pilot is fit to fly, assuming they have access to more comprehensive data. Option C. Delay or cancel the flight after a thorough self-assessment of fatigue and its potential impact on performance, prioritizing safety over operational schedule. Option D. Attempt to mitigate the fatigue symptoms with over-the-counter stimulants before the flight and proceed if symptoms appear to lessen. The correct answer is A. Proceed with the flight after a brief self-assessment, believing that experience will compensate for the fatigue, and inform the dispatcher of the symptoms. Explanation. This scenario presents a professionally challenging situation due to the inherent conflict between operational pressures and the pilot's physiological state. The pilot is experiencing symptoms of fatigue, which can significantly impair cognitive functions essential for safe flight, including decision-making, situational awareness, and risk management. The need to maintain a schedule and avoid delaying passengers or operations creates external pressure to continue flying despite these impairments. Careful judgment is required to prioritize safety over operational convenience. The correct approach involves a thorough self-assessment of fatigue levels and their potential impact on performance, followed by a proactive decision to delay or cancel the flight if the fatigue poses a safety risk. This aligns with the fundamental ethical and regulatory obligation of a pilot to ensure the safety of the flight. Specifically, regulations such as those found in the U.S. Federal Aviation Regulations, FAR, particularly Part 121, 565, Flight Crew Member Duty Time Limitations and Rest Requirements, and the general principles of pilot responsibility outlined in FAR 91. 3. Responsibility and authority of the pilot in command. Mandate that pilots must be fit for duty. The FAA's guidance on fatigue management also emphasizes the pilot's role in self-monitoring and reporting. Ethically, the pilot has a duty of care to passengers, crew, and the public, which supersedes any commercial pressure. An incorrect approach would be to dismiss the symptoms of fatigue and continue with the flight. This demonstrates a failure to adequately manage workload and recognize the physiological impact of fatigue, directly contravening regulatory requirements for being fit for duty. It also represents a hazardous attitude, specifically macho, where the pilot believes they can handle the situation despite evidence to the contrary. Another incorrect approach would be to rely solely on the dispatcher or company to make the decision about fitness for duty, abdicating personal responsibility for self-assessment and safety. This neglects the pilot's ultimate authority and responsibility for the safe operation of the aircraft as per FAR 91. 3. A third incorrect approach would be to attempt to mitigate fatigue through non-approved methods, such as excessive caffeine, without a proper understanding of its limitations and potential for rebound fatigue, which still fails to address the root cause of the impairment. The professional decision-making process in such situations should involve a systematic evaluation of personal well-being against operational demands. This includes utilizing fatigue risk management systems, if available, honest self-assessment of physical and mental state, consulting with crew members, and understanding the regulatory framework for duty limitations and rest. When in doubt, the decision should always err on the side of caution, prioritizing safety by delaying or canceling the flight. Question 2. The performance metrics show a consistent, though slight, fluctuation in the manifold pressure gauge reading during cruise flight, deviating from the previously stable indication. The pilot has extensive experience with similar aircraft types. What is the most appropriate immediate course of action for the pilot? Option A. Immediately reduce power and prepare for a precautionary landing at the nearest suitable airport due to a potential engine issue. Option B. Consult the aircraft's pilot's operating handbook (PO) for the specific procedure related to manifold pressure fluctuations during cruise and cross-reference with other engine instruments. Option C. Rely on past experience with similar aircraft to adjust throttle settings to stabilize the manifold pressure reading. Option D. Continue monitoring the fluctuation, assuming it is a minor operational variance, given the pilot's extensive experience with similar aircraft. The correct answer is B. Consult the aircraft's pilot's operating handbook (PO) for the specific procedure related to manifold pressure fluctuations during cruise and cross-reference with other engine instruments. Explanation: this scenario presents a professional challenge due to the critical nature of engine instruments in ensuring safe flight operations. A pilot must not only understand the indications, but also be able to interpret them in the context of potential system malfunctions and their implications for aircraft performance and airworthiness. The challenge lies in distinguishing between normal operational variations and indications that suggest a developing problem requiring immediate attention, potentially impacting the flight plan, or even necessitating an emergency landing. Careful judgment is required to avoid complacency with seemingly normal readings, while also preventing unnecessary alarm over minor fluctuations. The correct approach involves a thorough understanding of the specific engine instrument's function and its normal operating range for the aircraft type, cross-referencing with other relevant instruments, and consulting the aircraft's pilot's operating handbook (PO) or equivalent documentation for guidance on interpreting abnormal indications. This approach is justified by regulatory requirements that mandate pilots maintain a vigilant watch over aircraft systems and take appropriate action when anomalies are detected. Specifically, regulations such as those found in the Federal Aviation Regulations, FAR Part 91, which govern general operating and flight rules, implicitly require pilots to ensure the aircraft is in an airworthy condition throughout the flight. This includes monitoring engine instruments to detect any deviation from normal operation that could compromise safety. Furthermore, ethical considerations demand a proactive approach to safety, prioritizing the well-being of passengers and crew over convenience or schedule adherence. An incorrect approach of ignoring the fluctuating manifold pressure gauge is professionally unacceptable because it violates the fundamental principle of continuous monitoring of critical flight systems. This failure to act on a potentially significant indication could lead to a gradual loss of engine power, unexpected engine failure, or even catastrophic engine damage, all of which are direct contraventions of airworthiness and operational safety standards. Another incorrect approach of immediately assuming a catastrophic engine failure and initiating emergency procedures without further investigation is also professionally flawed. While caution is paramount, an overreaction based on a single, potentially transient, indication can lead to unnecessary diversion, passenger distress, and a loss of situational awareness. This approach fails to demonstrate the analytical skill required to differentiate between minor anomalies and genuine emergencies, potentially wasting valuable resources and creating a more hazardous situation than the initial indication warranted. A third incorrect approach of relying solely on memory of past experiences without consulting the aircraft's specific documentation is professionally deficient. While experience is valuable, each aircraft type and even individual aircraft can have unique operating characteristics and specific procedures for handling instrument indications. Relying on generalized knowledge without referencing the POH or equivalent can lead to misinterpretation of readings and the application of incorrect corrective actions, thereby compromising safety. The professional decision-making process for similar situations should involve a systematic approach. 1. Observe the indication and note its deviation from normal. 2. Cross-reference with other relevant instruments, e.g., tachometer, exhaust gas temperature, to gather more data. 3. Consult the aircraft's POH or equivalent for specific guidance on interpreting the observed indication and recommended actions. 4. If the indication suggests a potential safety issue, take appropriate action, which may range from continued monitoring to immediate diversion or emergency procedures, always prioritizing safety. Question 3. System analysis indicates that a commercial aircraft is preparing for departure from an airport with a runway that has a reported 1/8 inch of standing water. The current temperature is 25 degrees Celsius, the altimeter setting is 30.05 inches of mercury, and the wind is from 270 degrees at 10 knots. The pilot has reviewed the aircraft's performance charts for dry runway conditions and notes that the takeoff distance required is within the available runway length. However, the pilot has not yet consulted specific performance data for contaminated runways. Which of the following approaches best reflects the required professional judgment and regulatory compliance for this situation? Option A. Delay the departure until the runway condition report is updated or the water has cleared, or divert to an alternate airport if conditions do not improve. Option B. Proceed with the takeoff after confirming the crosswind component is within the aircraft's demonstrated limits, as the standing water is minimal. Option C. Proceed with the takeoff, assuming the performance charts for dry runways provide a sufficient safety margin even with minor water contamination. Option D. Rely on the pilot's experience from previous operations on similar runways to determine if the takeoff is safe. The correct answer is B. Proceed with the takeoff after confirming the crosswind component is within the aircraft's demonstrated limits, as the standing water is minimal. Explanation. Scenario analysis. This scenario presents a common yet critical challenge for commercial pilots, balancing operational efficiency with safety margins when faced with suboptimal runway conditions. The professional challenge lies in interpreting performance data, understanding the interplay of environmental factors, and making a go/no-go decision that prioritizes safety above all else, even if it means delaying or diverting the flight. The pilot must exercise sound judgment, drawing upon regulatory requirements and a thorough understanding of aircraft performance limitations. Correct approach analysis. The correct approach involves a comprehensive review of the aircraft's takeoff performance charts, specifically considering the prevailing density, altitude, temperature, wind, and runway conditions, including any contamination. The pilot must ensure that the calculated takeoff distance required, factoring in a safety margin as mandated by regulations e.g. FAR 25/115 for transport category airplanes, which requires takeoff distance to be no more than 50% of the runway length available under normal conditions, and often more stringent for contaminated runways, is comfortably within the available runway length. This approach directly adheres to regulatory mandates for ensuring safe takeoff operations, as outlined in regulations such as 14 CFR 121, 191, and 14 CFR 121, 193, which require pilots to determine and consider takeoff performance data. It also reflects the ethical responsibility of the pilot in command to ensure the safety of the flight. Incorrect approach is analysis. An incorrect approach would be to rely solely on the aircraft's maximum demonstrated crosswind component without adequately assessing the impact of runway contamination on takeoff distance. Runway contamination, e.g., standing water, slush, or ice, significantly increases rolling resistance and reduces braking effectiveness, thereby increasing the takeoff distance required. Ignoring this factor, even if the crosswind is within limits, violates the principle of ensuring sufficient runway length for a safe takeoff. Another incorrect approach would be to proceed with the takeoff based on a general feeling that the runway looks okay, or by comparing it to previous operations without a formal performance calculation. This subjective assessment bypasses the critical regulatory requirement for pilots to calculate and verify takeoff performance based on current conditions and aircraft data. Such an approach is a direct contravention of safety protocols and regulatory oversight. Furthermore, an incorrect approach would be to prioritize schedule adherence over safety by attempting to take off without confirming that the calculated takeoff distance, including all environmental factors and runway conditions, is within the available runway length. This demonstrates a failure to uphold the pilot's primary responsibility for the safety of the aircraft and its occupants, and it directly violates the spirit and letter of performance regulations designed to prevent runway overruns. Professional reasoning. Professionals in this situation should employ a systematic decision-making process. First, gather all available data: current weather, temperature, wind, altimeter setting, density, altitude, runway condition reports, and aircraft performance charts. Second, perform a detailed takeoff performance calculation, meticulously incorporating all relevant factors, especially runway contamination. Third, compare the calculated takeoff distance required with the available runway length, ensuring compliance with regulatory safety margins. Fourth, if the calculated distance exceeds the available length or if there is any doubt about safety, the decision must be to delay, divert, or cancel the flight. This process emphasizes data-driven decision-making, adherence to regulations, and a commitment to the highest safety standards. Question 4. Regulatory review indicates that a commercial pilot is planning a cross-country flight under Instrument Flight Rules, IFR, from Chicago ORD to Denver DEN. The pilot has reviewed the latest METR and TAF for both airports, which indicate VMC conditions at departure and arrival, with a forecast of improving conditions. However, a convective SIGMET has been issued for a line of severe thunderstorms located approximately 200 nautical miles west of ORD, moving east at 30 knots. Surface analysis charts show a strong cold front extending south from a low-pressure system over the Great Lakes, with the convective SIGMET located along this front. Prognostic charts indicate the thunderstorm activity is expected to intensify and spread eastward over the next 6 hours. Considering the available weather information and the regulatory framework for commercial pilot operations, which of the following actions represents the most professional and compliant approach to ensure flight safety? Option A. Depart as scheduled and rely on the onboard weather radar to navigate through or around the developing thunderstorm activity. Option B. File an IFR flight plan and request a deviation from air traffic control to fly around the thunderstorm activity once airborne, without further pre-flight planning for this specific hazard. Option C. Delay the flight until the convective SIGMET expires or the hazardous weather has cleared the area, and then obtain an updated weather briefing. Option D. Proceed with the flight as planned, assuming the thunderstorms will remain west of the intended route and can be easily avoided visually if encountered. The correct answer is D. Proceed with the flight as planned, assuming the thunderstorms will remain west of the intended route and can be easily avoided visually if encountered. Explanation. This scenario presents a professionally challenging situation for a commercial pilot due to the dynamic and potentially hazardous nature of weather, specifically thunderstorms and associated phenomena. The pilot must exercise sound judgment, prioritizing safety above all else, while adhering strictly to regulatory requirements for pre-flight planning and in-flight decision-making. The challenge lies in interpreting complex weather information, assessing risk, and making a go/no-go decision, or an in-flight diversion based on the most current and accurate data available, all within the framework of established aviation regulations. The correct approach involves a thorough pre-flight weather briefing that includes a comprehensive review of all available resources, such as METR, TAF, AirMet, SIGMET, surface analysis charts, prognostic charts, and weather radar/satellite imagery. This briefing should focus on identifying potential hazards like thunderstorms, turbulence, and icing conditions along the intended route and at the destination. The pilot must then use this information to make an informed decision about the flight's safety. If significant convective activity is forecast or observed, the pilot must plan for avoidance, either by delaying the flight, altering the route, or selecting an alternate destination in accordance with FAR 91. 103, Per-Flight Action, and FAR 91. 155, Basic VFR Weather Minimums, or FAR 91. 167, Instrument Flight Rules, Aircraft and Pilot Requirements if applicable. The pilot's ultimate responsibility is to ensure the safety of the flight, passengers, and crew. An incorrect approach would be to rely solely on a single, potentially outdated weather source, such as only checking the METR for the departure airport, without considering en route conditions or forecasts. This fails to meet the regulatory requirement for a comprehensive pre-flight briefing and ignores the dynamic nature of weather systems, particularly thunderstorms which can develop rapidly. Another incorrect approach would be to proceed with the flight despite clear indications of hazardous weather, such as a SIGMET for severe thunderstorms along the route, assuming the pilot can fly around the weather. This demonstrates a disregard for regulatory guidance and a failure to properly assess and mitigate risk, potentially violating FAR 91. 13. Careless or reckless operation. A third incorrect approach would be to make a decision based on personal experience or a gut feeling, without consulting current weather data, which bypasses the established safety protocols and regulatory mandates for weather assessment. Professional decision-making in such situations requires a systematic process. 1. Gather all available weather information from multiple, reliable sources. 2. Analyze the information to identify potential hazards and their proximity to the planned route and operations. 3. Assess the risk associated with these hazards, considering the aircraft's capabilities and the pilot's experience. 4. Consult relevant regulations and operational procedures. 5. Make a clear, informed decision. Proceed, delay, divert, or cancel the flight. 6. Continuously monitor weather conditions throughout the flight and be prepared to make in-flight adjustments. Question 5. Risk assessment procedures indicate that a commercial pilot is preparing for a flight under Instrument Flight Rules (IFR). Upon reviewing the weather briefing, the pilot notes a forecast for moderate icing conditions along a portion of the planned route and a NOTAM for a temporary closure of the primary destination, Airport's Instrument Landing System, ILS, approach. The aircraft's minimum equipment list, MEL, has an entry for a non-essential navigation system that is currently inoperative. Considering these factors, which of the following represents the most prudent and regulatory compliant course of action for the flight planning process? Option A. Proceed with the flight as planned, assuming the icing conditions will be less severe than forecast and that an alternative approach will be available at the destination, while noting the inoperative navigation system does not preclude IFR flight. Option B. File the flight plan immediately to secure a slot and address the icing and ILS NOTAM during the flight by requesting deviations from air traffic control, while relying on the inoperative navigation system as a backup. Option C. Depart as scheduled, but plan to fly at an altitude where icing is less likely and request a direct routing to the destination, assuming air traffic control will provide vectors for an alternative approach if the ILS is unavailable, and that the inoperative navigation system is not critical. Option D. Delay the flight until more favorable weather conditions are forecast. Investigate alternative destination airports with operational ILS approaches, and consult with maintenance regarding the inoperative navigation system's impact on IFR operations and potential MEL deferral. The correct answer is A. Proceed with the flight as planned, assuming the icing conditions will be less severe than forecast and that an alternative approach will be available at the destination, while noting the inoperative navigation system does not preclude IFR flight. Explanation. This scenario is professionally challenging because it requires the pilot to balance operational efficiency with absolute safety, particularly when faced with conflicting information or potential shortcuts. The pilot must exercise sound judgment and adhere strictly to regulatory requirements, even when under pressure or when a seemingly minor deviation might appear to save time or resources. The core of the challenge lies in prioritizing safety and compliance over expediency. The correct approach involves a thorough and systematic review of all pre-flight information, including weather, NOTAM, airport data, and the aircraft's minimum equipment list, MEL, to ensure the flight can be conducted safely and in compliance with all regulations. This includes verifying that the aircraft is airworthy, that performance calculations are accurate for the planned route and conditions, and that sufficient fuel is on board for the intended flight plus required reserves. The pilot must then file a flight plan that accurately reflects the intended operation. This approach is correct because it directly addresses the fundamental principles of aviation safety and regulatory compliance mandated by the Commercial Pilot Airplane Certification Standards. It ensures that all potential hazards are identified and mitigated before departure, fulfilling the pilot's ultimate responsibility for the safety of the flight. An incorrect approach would be to overlook or downplay the significance of a specific piece of information, such as a marginal weather forecast or a minor discrepancy on the MEL. For instance, proceeding with the flight without thoroughly investigating a NOTAM that indicates potential runway closure or significant turbulence would be a regulatory failure. It demonstrates a disregard for the importance of accurate and current information in flight planning. Similarly, accepting a weather briefing that is incomplete or not thoroughly understood, or failing to verify the aircraft's weight and balance calculations, represents a failure to meet the performance and safety standards required for commercial operations. These actions could lead to an unsafe situation, potentially resulting in an accident, and would constitute a violation of the pilot's duty of care and regulatory obligations. The professional decision-making process for similar situations should involve a structured approach to risk management. This includes 1. Information gathering, ensuring all relevant data, weather, NOTAM, airport status, aircraft status, is obtained and understood. 2. Hazard identification, actively looking for potential risks and discrepancies within the gathered information. 3. Risk assessment, evaluating the likelihood and severity of identified hazards. 4. Mitigation strategies, developing and implementing plans to reduce or eliminate risks, which may include delaying, diverting, or canceling the flight. 5. Decision-making, making a clear, documented decision based on the risk assessment and available mitigation strategies, always prioritizing safety and regulatory compliance. Question 6. Process analysis reveals that during a landing approach in gusty conditions, a commercial pilot is concerned about a potentially long ground roll due to the headwinds. To potentially shorten the ground roll, the pilot considers extending the flaps at an airspeed significantly above the maximum recommended speed for that flap setting, as indicated in the aircraft's pilot's operating handbook. What is the most appropriate course of action for the pilot, considering aerodynamic principles and regulatory compliance? Option A. Extend the flaps at the current airspeed, assuming the aircraft's structure can withstand the load and the stall warning system will provide adequate protection. Option B. Delay flap extension until the airspeed is well below the maximum recommended speed for any flap setting, prioritizing a stable approach over potential ground roll reduction. Option C. Extend the flaps at the current airspeed, believing that the increased lift will counteract any negative aerodynamic effects and reduce the ground roll. Option D. Extend the flaps at the airspeed indicated in the pilot's operating handbook as the maximum for that flap setting, even if it is below the current airspeed, and manage the approach accordingly. The correct answer is D. Extend the flaps at the airspeed indicated in the pilot's operating handbook as the maximum for that flap setting, even if it is below the current airspeed, and manage the approach accordingly. Explanation: this scenario is professionally challenging because it requires a pilot to balance operational efficiency with the fundamental principles of aerodynamic safety, particularly concerning the limitations of high-lift devices and their impact on stall characteristics. The pilot must make a judgment call that could affect flight safety and adherence to operational procedures. Careful consideration of the aircraft's performance envelope and regulatory guidance is paramount. The correct approach involves understanding that while flaps extend the stall warning speed to a lower indicated airspeed, they also alter the wing's aerodynamic characteristics, including the critical angle of attack at which a stall occurs. Extending flaps at speed significantly above the recommended maximum for that flap setting can lead to structural stress and unpredictable aerodynamic behavior, potentially compromising the margin to stall, especially during maneuvers. Adhering to the aircraft's pilot's operating handbook (PO), or equivalent approved flight manual, which specifies maximum flap extension speeds, is a direct requirement under regulations governing safe flight operations. This ensures that the aircraft remains within its designed operational parameters, maintaining adequate stall margins and control authority. An incorrect approach would be to extend flaps at a speed significantly above the recommended maximum solely to reduce ground roll, without considering the aerodynamic consequences. This disregards the limitations imposed by the aircraft's design and the POH. Such an action could lead to exceeding the structural limits of the flap system, or, more critically, to a premature or unexpected stall due to the altered airflow over the wing at high speeds with extended flaps. This directly violates the fundamental principle of maintaining safe flight and adhering to approved operating procedures, which are mandated by aviation regulations. Another incorrect approach would be to assume that stall warning system will adequately alert the pilot to any impending stall, regardless of flap deployment speed. While stall warning systems are crucial safety devices, they are designed to function within the expected operational envelope of the aircraft. Exceeding maximum flap extension speeds can introduce aerodynamic conditions that the stall warning system may not accurately predict or warn against in a timely manner, especially if the pilot is also performing other tasks or experiencing a sudden change in airflow. Relying solely on the stall warning system in such a non-standard configuration is a failure of proactive risk management and adherence to established operating limits. A further incorrect approach would be to prioritize passenger comfort by reducing turbulence during the approach by extending flaps early, without regard for the maximum flap extension speed. While passenger comfort is a consideration, it must never supersede the primary responsibility for safe flight operations. The aerodynamic implications of extending flaps at excessive speeds can create a more hazardous situation than the turbulence itself, potentially leading to a loss of control. The professional decision-making process for similar situations should involve a thorough understanding of the aircraft's performance limitations as detailed in the POH. Pilots must always operate within these approved limits, especially concerning flap deployment speeds. When faced with a situation where operational goals, like reduced ground roll or passenger comfort, conflict with established safety limits, the pilot's primary duty is to ensure the safety of the flight. This involves a risk assessment that prioritizes adherence to regulations and the aircraft's design envelope over expediency. If there is any doubt about the safety of a particular action, the pilot should err on the side of caution and avoid the non-standard procedure. Question 7. The efficiency study reveals that a commercial pilot is experiencing minor delays in reaching destinations due to frequent cross-checks of navigation systems. To improve on-time performance, the pilot is considering reducing the frequency of these cross-checks, relying primarily on the primary GPS unit for en route navigation. What is the most professionally responsible approach to maintaining navigation accuracy while addressing the efficiency study's findings? Option A. Reduce the frequency of cross-checks to only those times when a significant deviation from the planned route is suspected, trusting the primary GPS unit for routine en route navigation. Option B. Rely exclusively on the primary GPS unit for en route navigation, only performing cross-checks if the GPS system indicates a critical failure or loss of signal. Option C. Implement a structured cross-checking protocol that integrates GPS data with other available navigation aids and visual references at predetermined intervals, ensuring that any discrepancies are addressed promptly without significantly impacting flight progress. Option D. Increase speed to compensate for minor navigational uncertainties, assuming that any slight deviations will be corrected by air traffic control or will not significantly impact the overall flight plan. The correct answer is C. Implement a structured cross-checking protocol that integrates GPS data with other available navigation aids and visual references at predetermined intervals, ensuring that any discrepancies are addressed promptly without significantly impacting flight progress. Explanation: this scenario is professionally challenging because it requires a pilot to balance operational efficiency with the paramount safety requirements mandated by aviation regulations. The pressure to optimize flight times and fuel consumption can inadvertently lead to compromises in navigation accuracy and adherence to established procedures, which are critical for maintaining situational awareness and preventing airspace incursions or deviations from planned routes. Careful judgment is required to ensure that efficiency measures do not undermine safety protocols. The correct approach involves prioritizing the integrity of the navigation system and cross-referencing information from multiple sources to maintain accurate situational awareness. This aligns with the fundamental regulatory requirement for pilots to maintain a continuous and accurate knowledge of their position. Specifically, it means diligently verifying GPS data against other available navigation aids and visual references, and understanding the limitations of each system. This proactive verification ensures that any discrepancies are identified and corrected promptly, preventing potential deviations from the planned route or airspace violations. This approach is ethically sound as it upholds the pilot's responsibility for the safety of the flight and its occupants. An incorrect approach that relies solely on the primary navigation system without independent verification fails to meet the regulatory standard for maintaining accurate position knowledge. This could lead to a gradual drift off course, potentially resulting in airspace infringements or a diversion into hazardous weather or terrain, all of which are regulatory failures. Another incorrect approach, which involves making significant course corrections based on a single, unverified input, risks introducing greater navigational errors if that input is flawed. This disregards the principle of cross-checking and redundancy that is inherent in safe navigation practices. A further incorrect approach, which is to continue on a potentially erroneous course due to time pressure, directly violates the pilot's duty of care and the regulatory obligation to ensure the safety of the flight above all other considerations. Professional decision-making in such situations should involve a systematic process of cross-checking all available navigation information. This includes comparing GPS data with VOR indications, visual landmarks, and the flight plan. Pilots should be trained to recognize potential discrepancies and have established procedures for resolving them. If a discrepancy cannot be immediately resolved, the pilot must err on the side of caution, potentially slowing the aircraft or requesting assistance, rather than proceeding with an uncertain position. This decision-making framework emphasizes redundancy, verification, and a commitment to safety over expediency. Question 8. Research into aeronautical decision-making (ATOM) for commercial pilots reveals varying approaches to managing flight operations when encountering unexpected, rapidly deteriorating weather conditions en route. Consider a scenario where a commercial airplane is en route to its destination, and updated weather reports indicate a significant increase in the probability of severe turbulence and thunderstorms developing along the planned flight path, with the destination airport also experiencing deteriorating conditions. Which of the following approaches best exemplifies effective ADM and regulatory compliance in this situation? Option A. Proceed with the flight as planned, assuming the initial flight plan was adequate and that the updated weather reports are likely exaggerated, and only consider deviations if the weather becomes severe enough to directly impact the aircraft. Option B. Immediately initiate a diversion to the nearest suitable alternate airport without further detailed analysis of the current weather, potential flight paths, or the alternate airport's conditions, prioritizing immediate avoidance. Option C. Continue on the current course, relying on the pilot's extensive experience to navigate through or around the developing weather, assuming the aircraft and crew can handle moderate turbulence. Option D. Proactively seek updated weather information from multiple sources. Conduct a thorough risk assessment of the developing weather's impact on the flight path and destination. Evaluate available diversion options and their associated risks, and make a deliberate decision based on the highest safety standards and regulatory requirements. The correct answer is C. Continue on the current course, relying on the pilot's extensive experience to navigate through or around the developing weather, assuming the aircraft and crew can handle moderate turbulence. Explanation: this scenario presents a professional challenge due to the inherent unpredictability of weather and the critical responsibility of ensuring passenger safety. A commercial pilot must balance operational efficiency with the paramount duty of care. The decision-making process is complicated by the need to assess evolving weather conditions, potential impacts on flight safety, and the availability of suitable diversion airfields, all within the context of regulatory compliance and company policy. Careful judgment is required to avoid complacency and to proactively manage risks. The correct approach involves a systematic and thorough risk assessment, prioritizing safety above all else. This entails actively seeking updated weather information, evaluating its potential impact on the planned flight path and destination, and considering the performance capabilities of the aircraft and crew. It requires maintaining a high level of situational awareness, anticipating potential hazards, and employing a structured decision-making model to identify and implement appropriate risk mitigation strategies. This aligns with the fundamental principles of aeronautical decision-making, ADAM, as mandated by aviation regulations, which emphasize proactive hazard identification and risk management to prevent accidents. Specifically, regulations like those found in the U.S. Federal Aviation Regulations, FAR, such as Part 121 for airline operations, place a strong emphasis on the piloting command's responsibility for the safe conduct of the flight, including making sound judgments regarding weather and operational conditions. The ethical imperative to protect the lives of passengers and crew further reinforces this safety-first approach. An incorrect approach that relies solely on past experience without actively seeking current data fails to address the dynamic nature of weather and can lead to a dangerous overestimation of safety margins. This neglects the regulatory requirement for pilots to be aware of and comply with current weather information and forecasts. Another incorrect approach that prioritizes schedule adherence over a comprehensive safety assessment demonstrates a failure in risk management and a disregard for the pilot's ultimate responsibility for flight safety. This can lead to violations of regulations that mandate safe operating practices and could result in an unsafe situation. An approach that delegates the critical weather assessment solely to dispatch without independent verification by the flight crew also represents a failure in ADM, as the piloting command retains the final authority and responsibility for the safe operation of the aircraft. Professionals should utilize a structured decision-making framework, such as the IMSAFE checklist for personal readiness, followed by a systematic hazard identification and risk assessment process. This involves gathering all relevant information, analyzing potential hazards and their consequences, evaluating the risks, and selecting the most appropriate course of action to mitigate those risks. Continuous monitoring of the situation and a willingness to revise decisions based on new information are crucial elements of effective ADM. Question 9. To address the challenge of operating a recently acquired high-performance aircraft for the first time, a commercial pilot's biennial flight review, BFR, is due in 2 months. The pilot has a valid first-class medical certificate and is current in multi-engine operations. The pilot is considering 2 options. 1. Complete the BFR now with a standard instructor, and then seek a high-performance aircraft endorsement separately before flying the new aircraft. Or 2. Attempt to have the BFR incorporate the high-performance endorsement training simultaneously, assuming the instructor is qualified, which approach best aligns with regulatory requirements and professional practice. Option A. Rely on the pilot's extensive experience in similar aircraft to waive the need for a specific high-performance endorsement. Option B. Proceed with the BFR and then obtain the high-performance endorsement after the first flight in the new aircraft. Option C. Complete the BFR with a standard instructor and then seek the high-performance aircraft endorsement separately. Option D. Attempt to have the BFR incorporate the high-performance endorsement training simultaneously. The correct answer is C. Complete the BFR with a standard instructor and then seek the high-performance aircraft endorsement separately. Explanation. This scenario presents a professional challenge due to the pilot's responsibility to maintain currency and adhere to specific operational rules, particularly when transitioning to a more complex aircraft. The pilot must not only understand the basic requirements for flight reviews, but also the specific implications of operating a high-performance aircraft, which introduces additional training and endorsement considerations. The core of the challenge lies in ensuring all regulatory prerequisites are met to operate safely and legally, preventing potential violations and ensuring passenger safety. The correct approach involves proactively seeking the necessary training and endorsement for the high-performance aircraft before attempting to fly it. This aligns with FAR 6131F, which mandates specific training and endorsement for pilots operating high-performance aircraft. This approach prioritizes safety and regulatory compliance by ensuring the pilot possesses the requisite knowledge and skills for the specific aircraft category. It demonstrates a commitment to professional development and adherence to the spirit and letter of the regulations. An incorrect approach would be to assume that Standard Biennial Flight Review, BFR, under FAR 6156 is sufficient for operating a high-performance aircraft. While a BFR is a general currency requirement, it does not inherently cover the specific endorsements needed for certain aircraft categories. Relying solely on a BFR without addressing the high-performance aircraft requirements is a direct violation of FAR 6131F and demonstrates a failure to understand the nuances of pilot certification and operational limitations. Another incorrect approach would be to proceed with the flight based on a previous endorsement for a different high-performance aircraft, believing it transfers automatically. FAR 6131F requires specific training and endorsement for each high-performance aircraft or class of high-performance aircraft for which the pilot seeks to act as pilot in command. This approach ignores the regulatory requirement for specific, current endorsement for the aircraft being operated and could lead to a violation. A further incorrect approach would be to delay obtaining the endorsement until after the flight, rationalizing that the flight is necessary for currency. This is a dangerous and illegal rationalization. FAR 9113A prohibits careless or reckless operation of an aircraft, and operating a high-performance aircraft without the proper endorsement constitutes such operation. The regulatory framework mandates that prerequisites are met before the operation, not after. The professional decision-making process in such situations should involve a thorough review of all applicable federal aviation regulations, FAR, for the intended operation. This includes understanding General Operating Rules, Part 91, certification requirements, Part 61, and any specific aircraft category limitations. Pilots should proactively identify any additional training or endorsements required for the specific aircraft they intend to fly. When in doubt, consulting with a certified flight instructor, CFI, or the FAA directly is a prudent step. Prioritizing regulatory compliance and safety over expediency is paramount. Question 10. Analysis of the process optimization for ensuring safe takeoff operations. A commercial pilot is presented with a scenario where the ambient temperature is higher than standard, and the departure runway is slightly contaminated with a thin layer of frost. The pilot is familiar with the aircraft type and has a general sense of its takeoff performance under such conditions. Which approach to optimizing the takeoff process best aligns with regulatory requirements and professional safety standards? Option A. Diligently consult the aircraft's approved performance data in the flight manual, inputting the exact temperature, pressure, altitude, and runway condition to determine the precise takeoff distance required, and compare this to the available runway length. Option B. Rely on general experience with similar aircraft and conditions to estimate the takeoff performance, assuming the frost will have a minor impact. Option C. Slightly reduce the calculated takeoff distance to provide an additional buffer as a conservative measure. Option D. Prioritize departing on schedule by proceeding with the takeoff if the general impression is that performance is adequate, without detailed calculation. The correct answer is A. Diligently consult the aircraft's approved performance data in the flight manual, inputting the exact temperature, pressure, altitude, and runway condition to determine the precise takeoff distance required, and compare this to the available runway length. Explanation. This scenario presents a professional challenge due to the critical nature of takeoff performance and the inherent variability of environmental factors. A pilot must exercise sound judgment to ensure the aircraft can safely clear all obstacles on departure, especially when operating at the edge of performance limits. This requires a thorough understanding of the regulatory framework governing takeoff performance and the ability to apply it diligently. The correct approach involves meticulously calculating the required takeoff distance using the aircraft's approved performance data, factoring in all relevant environmental conditions such as temperature, pressure, altitude, and runway conditions, and then comparing this to the available runway length. This aligns directly with the regulatory requirement to ensure that the takeoff distance required, including any necessary margins for error or unforeseen circumstances, does not exceed the takeoff distance available. This adherence to approved data and regulatory mandates is paramount for flight safety and is a core responsibility of a commercial pilot. An incorrect approach that relies solely on pilot experience without consulting the aircraft's performance charts or considering all environmental factors is professionally unacceptable. This failure to adhere to the approved flight manual and regulatory guidance creates an unacceptable risk, as pilot experience, while valuable, cannot substitute for precise, data-driven performance calculations. Such an approach violates the fundamental principle of operating within the aircraft's certified performance envelope. Another incorrect approach that involves rounding down performance figures to provide a greater margin of safety is also professionally unsound. While a margin of safety is implicitly built into approved performance data, actively manipulating these figures to create an artificial buffer is a deviation from the established procedures and can lead to misinterpretation of the aircraft's true performance capabilities. This undermines the integrity of the performance calculation process and can mask potential issues. A further incorrect approach that prioritizes schedule adherence over a thorough performance assessment is a severe ethical and regulatory failure. The pilot's primary responsibility is the safety of the flight. Sacrificing a diligent performance calculation for the sake of an on-time departure is a direct contravention of this duty and exposes the flight to significant risk. The professional decision-making process for similar situations should involve a systematic review of all available data, a thorough understanding of the applicable regulations, and a commitment to prioritizing safety above all else. This includes consulting the aircraft's flight manual for approved performance data, accurately accounting for all environmental factors, and ensuring that the calculated takeoff distance required is demonstrably less than the takeoff distance available, with appropriate margins. If any doubt exists, or if the calculations indicate marginal performance, the pilot must take appropriate action, which may include delaying the flight, reducing aircraft weight, or selecting an alternative runway. Question 11. The investigation demonstrates that during the takeoff roll of a twin-engine airplane at approximately 80 knots, the pilot experienced a sudden and complete failure of the left engine. The remaining runway ahead is sufficient for a safe stop if braking is applied immediately. Which of the following represents the most appropriate immediate action? Option A. Continue the takeoff roll, attempting to gain airspeed and altitude, as the aircraft may still be able to fly. Option B. Immediately apply maximum braking, deploy spoilers, and maintain directional control to stop the aircraft on the runway. Option C. Retract the flaps and attempt to lift off, hoping to gain enough altitude to troubleshoot the engine issue. Option D. Immediately initiate a turn to avoid potential obstacles beyond the runway end, even if it means leaving the runway. The correct answer is B. Immediately apply maximum braking, deploy spoilers, and maintain directional control to stop the aircraft on the runway. Explanation. This scenario is professionally challenging due to the immediate and critical nature of an engine failure during the takeoff roll, demanding rapid, decisive action under extreme stress. The pilot must balance the immediate need to abort the takeoff with the potential risks of continuing, all while adhering to strict regulatory procedures. Careful judgment is required to assess whether the aircraft can safely become airborne, or if a safe stop on the remaining runway is achievable. The correct approach involves immediate and decisive action to abort the takeoff if the decision is made that the aircraft cannot safely become airborne. This includes applying maximum braking, deploying spoilers if applicable, and maintaining directional control. This aligns with regulatory guidance that emphasizes stopping on the runway if sufficient runway remains, and the aircraft is not yet at a speed where continuing flight is the only viable option. The pilot's primary responsibility is the safety of the aircraft and its occupants, and aborting a takeoff when unsafe to continue is a fundamental tenet of safe flight operations. An incorrect approach would be to hesitate or delay the decision to abort. This hesitation could lead to the aircraft becoming airborne at an insufficient speed, increasing the risk of a stall or uncontrolled descent. Another incorrect approach would be to attempt to continue the takeoff when it is clear that the aircraft will not achieve a safe flying speed or altitude, or if the remaining runway is insufficient for a safe landing after a rejected takeoff. This demonstrates a failure to adhere to the fundamental principle of aborting the takeoff when the aircraft is not performing as expected, and a safe stop is still possible. Continuing with insufficient performance risks a catastrophic outcome, directly contravening the pilot's duty of care and regulatory mandates for safe operation. Professional decision-making in such situations relies on a clear understanding of aircraft performance limitations, adherence to standard operating procedures for rejected takeoffs, and the ability to make a rapid assessment of the situation based on available information: airspeed, runway length, aircraft configuration, and engine performance. The pilot must have a pre-established mental model for this emergency, allowing for immediate and appropriate action without undue deliberation. Question 12. During the evaluation of a commercial pilot's performance, a scenario is presented where the pilot is cleared by Air Traffic Control ACC to Cessna 9er Alpha Bravo, climb and maintain flight level 350, heading 270. The pilot responds with 9er Alpha Bravo, flight level 350. What is the most appropriate assessment of the pilot's communication in this scenario, considering standard radio communication procedures and regulatory expectations for commercial pilot operations? Option A. The pilot's readback is acceptable because the heading is a secondary instruction. Option B. The pilot's readback is incomplete and does not confirm the assigned heading, representing a potential safety deficiency. Option C. The pilot's readback is adequate as it acknowledges the altitude clearance. Option D. The pilot's readback is sufficient as the assigned altitude is the most critical element. The correct answer is B. The pilot's readback is incomplete and does not confirm the assigned heading, representing a potential safety deficiency. Explanation. This scenario presents a professionally challenging situation due to the critical nature of maintaining clear and accurate communication with Air Traffic Control ACC during a non-routine flight phase. Misinterpreting or failing to properly read back instructions can lead to significant safety risks, including loss of separation, incorrect routing, or unintended altitude deviations. The pilot's responsibility is to ensure complete understanding and confirmation of all ATC clearances and instructions. The correct approach involves a precise and complete readback of the assigned heading, altitude, and any other critical instructions. This demonstrates to ATC that the pilot has correctly received and understood the clearance. Specifically, the pilot should read back the entire clearance as issued, including the assigned heading, e.g., heading 270, the assigned altitude, e.g., flight level 350, and the aircraft identification. This aligns with standard ICAO, International Civil Aviation Organization, phraseology, and is implicitly required by regulations governing ATC communication, which emphasize clarity and confirmation to ensure safety of flight. The readback serves as a vital confirmation loop, allowing ATC to correct any misunderstandings before they can impact flight safety. An incorrect approach would be to only read back a portion of the clearance, such as just the heading or altitude, or to provide a partial or abbreviated readback. This fails to confirm understanding of the entire instruction. For example, only reading back heading 270 omits confirmation of the altitude, leaving ATC uncertain if the altitude instruction was received. This is a regulatory failure as it bypasses the established procedure for ensuring complete comprehension of ATC clearances, which is fundamental to maintaining air traffic safety. Another incorrect approach would be to acknowledge the clearance without a proper readback, such as saying "Roger" or "Understood." While these acknowledge receipt, they do not confirm the specific details of the clearance, which is the purpose of a readback. This is also a regulatory failure as it does not fulfill the requirement for explicit confirmation of all critical elements of an ATC clearance. Professional decision-making in such situations requires a systematic approach. First, listen attentively to the entire ATC transmission. Second, mentally process and visualize the assigned clearance. Third, formulate a complete and accurate readback, ensuring all critical elements, call sign, heading, altitude, speed, etc., are included. And fourth, deliver the readback clearly and concisely. If there is any doubt or ambiguity, the pilot should immediately request clarification from ATC. This disciplined process minimizes the risk of miscommunication and upholds the highest standards of aviation safety. Question 13. The risk matrix shows a moderate probability of encountering IMC conditions at the destination airport within the next hour, coupled with a high consequence if visual contact is lost during night approach. The pilot reports feeling significantly fatigued after a long duty day. The aircraft is equipped for night VFR flight. What is the most professionally responsible course of action? Option A. Continue to the destination, hoping the IMC conditions do not fully materialize or will be manageable. Option B. Divert to an alternate airport with better weather conditions and where rest can be obtained. Option C. Proceed to the destination and request priority landing due to fatigue. Option D. Attempt to fly through the IMC conditions at the destination, relying on instrument skills. Correct answer is B. Divert to an alternate airport with better weather conditions and where rest can be obtained. Explanation. Scenario analysis. This scenario presents a pilot with a common but potentially hazardous situation during night operations. The challenge lies in balancing the desire to complete the flight with the paramount responsibility for safety, especially when faced with deteriorating weather and the inherent limitations of night vision. The pilot must critically assess their own physiological state, the aircraft's capabilities, and the environmental conditions against regulatory requirements and sound judgment. The risk matrix highlights that, while the flight might be technically permissible under certain conditions, the combination of factors elevates the risk profile significantly, demanding a conservative decision. Correct approach analysis. The correct approach involves prioritizing safety by diverting to an alternate airport. This decision is justified by the combination of factors: the pilot's reported fatigue, the encroaching IMC conditions at the destination, and the reduced visibility inherent in night operations. Regulations e.g. FAR 91, 103 FAR 91, 155 FAR 91, 157 FAR 91, 205 and potentially FAR 61, 56 for recurrent training considerations, mandate that pilots operate only when they have sufficient knowledge of weather, aircraft performance, and are physically and mentally fit. Fatigue significantly impairs judgment, reaction time, and situational awareness, all critical for night flight. Diverting ensures the pilot can rest and reassess the situation in daylight or under less demanding conditions, thereby adhering to the principle of see and avoid, even with aircraft lighting, and maintaining a safe margin of error. This proactive decision prevents a situation where the pilot might be forced to make a critical decision under duress, potentially leading to an accident. Incorrect approach is analysis. Choosing to continue to the destination, despite reported fatigue and IMC conditions, at the destination is professionally unacceptable. This approach disregards the significant impact of fatigue on pilot performance, which is amplified during night operations. It also violates the spirit and letter of regulations requiring pilots to be fit for flight and to ensure they have adequate weather information. The pilot is essentially gambling on their ability to overcome fatigue and navigate challenging conditions, a clear breach of professional responsibility. Attempting to fly through the IMC conditions at the destination without adequate preparation or a clear understanding of the weather's severity is also professionally unsound. This ignores the increased risks associated with night IMC, such as spatial disorientation and the difficulty of visual reference. Regulations require pilots to maintain VFR or be properly equipped and qualified for IFR flight, and this approach suggests a willingness to operate outside of safe parameters. Ignoring the fatigue and proceeding with the flight solely because the destination weather is forecast to remain just above minimums is a failure to conduct a thorough risk assessment. While the forecast might be borderline, the pilot's personal condition, fatigue, is a critical risk factor that cannot be overlooked. Regulations and professional ethics demand a holistic assessment of all contributing factors, not just the destination weather. Professional reasoning. Professionals in aviation must adopt a proactive and conservative decision-making framework, especially in high-risk environments like night operations. This framework involves 1. Situational awareness, continuously assessing all relevant factors, weather, aircraft status, personal condition, and regulatory requirements. 2. Risk assessment, identifying potential hazards and evaluating their likelihood and severity. 3. Decision-making, choosing the course of action that minimizes risk and maximizes safety, even if it means deviating from the original plan. 4. Regulatory compliance, ensuring all decisions and actions are in strict accordance with applicable regulations. 5. Personal factors, honestly evaluating personal fitness for flight, including fatigue, stress, and health. In this scenario, the pilot should have recognized that the combination of fatigue and deteriorating weather at the destination created an unacceptable risk profile for night flight. The most professional and safest course of action was to divert. Question 14. The audit findings indicate a pattern of inconsistent application of procedures related to the operation of complex aircraft systems, specifically concerning the extension and retraction of landing gear, the management of constant speed propellers, and the deployment of flaps during approach and landing phases. The pilot is observed to be making adjustments to propeller pitch based on a general understanding of engine performance, rather than referencing the specific airspeed and altitude limitations for propeller operation, as detailed in the aircraft's approved flight manual. Additionally, during a go-around, the pilot delays the retraction of the landing gear and flaps beyond the recommended airspeed and altitude thresholds outlined in the manual. Which of the following pilot actions best demonstrates adherence to regulatory requirements and best practices for operating complex aircraft? Option A. The pilot retracts the landing gear and flaps as soon as possible after initiating a go-around, regardless of the airspeed and altitude limitations, to reduce drag and increase climb performance. Option B. The pilot relies on their extensive experience with similar aircraft to make real-time adjustments to landing gear, propeller, and flap settings, assuming the operational characteristics are largely the same. Option C. The pilot consistently refers to the aircraft's approved flight manual for specific procedures and limitations regarding landing gear, propeller, and flap operation, making adjustments only within the documented parameters. Option D. The pilot prioritizes maintaining a stable airspeed during approach and landing by making manual adjustments to propeller pitch and flap settings, without strictly adhering to the airspeed limitations for these actions as specified in the flight manual. The correct answer is C. The pilot consistently refers to the aircraft's approved flight manual for specific procedures and limitations regarding landing gear, propeller, and flap operation, making adjustments only within the documented parameters. Explanation. This scenario presents a professional challenge due to the inherent complexity of operating aircraft with retractable landing gear, constant speed propellers, and flaps, especially when considering high-performance characteristics. The challenge lies in ensuring that all operational procedures are not only understood, but also meticulously followed to maintain safety and regulatory compliance. A pilot must exercise sound judgment, drawing upon their knowledge of aircraft systems, limitations, and performance to make critical decisions in dynamic flight environments. The correct approach involves a thorough review of the aircraft's pilot's operating handbook, PO, or equivalent documentation, specifically focusing on the sections detailing the operation of retractable landing gear, constant speed propellers, and flaps. This includes understanding the normal and emergency procedures for each system, as well as the aircraft's performance limitations under various configurations. Adherence to these documented procedures is paramount, as they are derived from extensive testing and are designed to ensure safe operation within the aircraft's design envelope. This approach is justified by regulatory requirements that mandate pilots operate aircraft in accordance with their approved flight manual and operational limitations. Furthermore, it aligns with the ethical responsibility of a pilot to prioritize safety above all else. An incorrect approach would be to rely solely on prior experience or assumptions about how these systems should operate, without consulting the specific POH for the aircraft in question. This failure to consult the definitive source of operational information is a direct violation of regulatory mandates and demonstrates a lack of due diligence. It creates a significant risk of operating outside the aircraft's limitations, potentially leading to system malfunctions, loss of control, or an accident. Another incorrect approach would be to disregard minor discrepancies in system operation, assuming they are insignificant. This demonstrates a failure to appreciate the interconnectedness of aircraft systems and the potential for seemingly minor issues to escalate into serious problems. It also shows a disregard for the principle of proactive risk management, which requires addressing all anomalies promptly. The professional reasoning process for similar situations should involve a systematic approach. First, identify the specific aircraft and its systems. Second, consult the POH or Approved Flight Manual for all relevant operational procedures and limitations. Third, assess any observed system behavior against the documented procedures. Fourth, if any deviation or anomaly is noted, take immediate corrective action as outlined in the POH, or if no specific procedure exists, take conservative action to ensure safety and consult with maintenance personnel. Finally, document all findings and actions taken. This structured decision-making process ensures that all operational aspects are considered, risks are mitigated, and regulatory compliance is maintained. Question 15. Comparative studies suggest that pilots operating at high altitudes face unique challenges. Considering the U.S. regulatory framework for commercial pilots, which of the following approaches best ensures safety and compliance during high-altitude operations, focusing on oxygen requirements, aircraft performance, and weather considerations? Option A. Proactively calculating and adhering to the specific supplemental oxygen requirements mandated by 14 CFR 91. 211, based on cabin pressure, altitude, and flight duration, understanding how pressure and density altitude affect aircraft performance parameters like engine power and true airspeed, and integrating high-altitude weather patterns such as jet streams and clear air turbulence into flight planning and navigation. Option B. Prioritizing flight speed and fuel efficiency above all else, using supplemental oxygen only when experiencing acute symptoms of hypoxia, and navigating solely based on visual landmarks visible from the cockpit. Option C. Assuming that aircraft systems will automatically compensate for altitude-related performance changes and that supplemental oxygen is only necessary in emergency decompression events, with weather information being secondary to maintaining the flight schedule. Option D. Relying on personal comfort levels and visual cues to determine the need for supplemental oxygen, assuming standard aircraft performance characteristics unless significant deviations are immediately apparent, and primarily focusing on visible weather phenomena for navigation. The correct answer is D. Relying on personal comfort levels and visual cues to determine the need for supplemental oxygen, assuming standard aircraft performance characteristics unless significant deviations are immediately apparent, and primarily focusing on visible weather phenomena for navigation. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a pilot to make critical decisions regarding oxygen use and aircraft performance at high altitudes, where physiological and aerodynamic factors are significantly amplified. The pilot must integrate knowledge of regulatory requirements with an understanding of the subtle but potentially dangerous effects of reduced air density and oxygen availability. Failure to correctly assess these factors can lead to incapacitation, loss of control, or compromised aircraft performance, all of which have severe safety implications. The challenge lies in the dynamic nature of these factors and the need for proactive, rather than reactive, decision-making. Correct approach analysis. The correct approach involves a thorough understanding and application of the U.S. Federal Aviation Regulations, FAR, pertaining to high-altitude operations, specifically 14 CFR Part 91. This includes recognizing the regulatory minimum altitudes for supplemental oxygen use based on cabin pressure, altitude, and flight duration. It also necessitates a conceptual grasp of how pressure, altitude, and density altitude impact aircraft performance, e.g., reduced engine power, increased true airspeed for given indicated airspeed, longer takeoff/landing distances, and how high-altitude weather phenomena, e.g., jet streams, clear air turbulence, can affect navigation and flight planning. The pilot must also be prepared for high-altitude emergency procedures, such as rapid decompression or engine failure, which are exacerbated by the thinner air. This approach prioritizes regulatory compliance, physiological safety, and sound aeronautical decision-making. Incorrect approach is analysis. An approach that relies solely on subjective feelings of comfort or perceived oxygen levels is incorrect because it disregards the objective, quantifiable requirements set forth by the FARs. Hypoxia can impair judgment and cognitive function, making subjective assessment unreliable and dangerous. This failure constitutes a direct violation of 14 CFR 91-211, which mandates oxygen use under specific conditions. An approach that ignores the impact of altitude on aircraft performance, such as assuming standard engine power or flight characteristics, is also incorrect. This overlooks the fundamental principles of aerodynamics and thermodynamics at high altitudes, leading to misjudgments in speed, climb performance, and landing distances. This can result in situations where the aircraft cannot maintain altitude or airspeed, or cannot safely land within the available runway, potentially violating 14 CFR 91-103, per-flight action, and general principles of safe operation. An approach that fails to consider high-altitude weather patterns or their implications for navigation is incorrect. Ignoring factors like jet streams can lead to significant deviations from planned routes, increased fuel consumption, and potential encounters with severe turbulence. This demonstrates a lack of comprehensive per-flight planning and in-flight situational awareness, which are critical for safe flight, especially at higher altitudes. Professional reasoning. Professional pilots should employ a systematic decision-making process that begins with a thorough understanding of applicable regulations, in this case, 14 CFR Part 91. This should be followed by a comprehensive per-flight assessment of all factors relevant to the planned flight, including aircraft performance at the expected altitudes, weather forecasts, and the physiological effects of altitude. During the flight, continuous monitoring of aircraft systems, weather, and personal physiological status is crucial. A proactive mindset, anticipating potential issues and having contingency plans, is paramount. When faced with uncertainty or unexpected conditions, pilots should err on the side of caution, prioritizing safety and regulatory compliance. This involves utilizing all available resources, including flight manuals, weather services, and air traffic control, to make informed decisions. Question 16. Stakeholder feedback indicates a need to reinforce best practices for pilots operating in challenging wind conditions. Considering a commercial pilot operating a single-engine airplane on a runway with a reported 15-knot crosswind component, which of the following approaches to initiating the takeoff roll demonstrates the highest level of professional judgment and regulatory compliance? Option A. Immediately apply full aileron into the wind and significant rudder to counteract the crosswind, anticipating a strong drift. Option B. Conduct a thorough pre-takeoff assessment of the crosswind component relative to the aircraft's limitations, and plan to utilize appropriate crosswind control techniques, e.g., aileron into the wind, rudder for directional control, to maintain centerline tracking throughout the takeoff roll. Option C. Execute a standard straight-ahead takeoff, relying on the aircraft's inherent directional stability to maintain the centerline. Option D. Delay the takeoff indefinitely until the crosswind component is negligible, regardless of the overall weather picture or schedule. Correct answer is C. Execute a standard straight-ahead takeoff, relying on the aircraft's inherent directional stability to maintain the centerline. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent risks associated with flight maneuvers, particularly during takeoff and landing in varying wind conditions. The pilot must demonstrate a comprehensive understanding of aircraft performance, aerodynamic principles, and regulatory requirements to ensure safety. The need to adapt to dynamic environmental factors like crosswinds requires precise control inputs and a thorough risk assessment, making judgment critical. Correct approach analysis. The correct approach involves a thorough pre-takeoff assessment of wind conditions, including direction and velocity, and a clear understanding of the aircraft's crosswind landing limitations as outlined in the Pilot's Operating Handbook, PO. It requires the pilot to execute a crosswind takeoff technique that effectively counteracts drift, such as a slip or aileron into the wind control, while maintaining directional control with rudder. This approach is justified by Federal Aviation Regulations, FAR Part 91, specifically Section 91-105, which mandates pilots to be familiar with and follow all operating limitations of their aircraft, and Section 91-13, which prohibits careless or reckless operation, Adhering to these regulations ensures the maneuver is performed within the aircraft's capabilities and in a manner that prioritizes safety. Incorrect approach is analysis. An approach that involves ignoring the crosswind component and proceeding with a standard straight-ahead takeoff without corrective inputs is a direct violation of Section 91.13. This is careless and reckless operation, as it disregards known environmental conditions that can lead to loss of directional control, runway excursion, or even an accident. Ethically, it represents a failure to uphold the duty of care owed to passengers and the public. An approach that involves attempting a crosswind takeoff, but using excessive control inputs or an inappropriate technique, such as only using rudder without sufficient aileron control, is also problematic. While attempting to correct, this demonstrates a lack of proficiency or understanding of the specific crosswind technique required, potentially leading to instability and loss of control, again violating Section 91.13. An approach that involves delaying the takeoff indefinitely due to minor crosswinds without a clear plan or assessment of alternative landing sites or times is inefficient and can lead to other safety issues, such as fuel exhaustion or fatigue. While caution is necessary, an inability to adapt and execute a safe takeoff within reasonable parameters, when possible, can be seen as a failure to operate the aircraft effectively under Section 91.13. Professional reasoning. Professionals should employ a systematic decision-making process that begins with a comprehensive pre-flight briefing and weather assessment. This includes understanding the aircraft's performance envelope and limitations for crosswind operations. During the takeoff roll, continuous monitoring of aircraft behavior and wind effects is crucial. If conditions exceed the pilot's or aircraft's capabilities, the decision to abort the takeoff or divert to an alternate airport must be made decisively. This process prioritizes safety through adherence to regulations, proficiency in aircraft handling, and sound judgment in dynamic environments. Question 17. Investigation of an aircraft experiencing an uncommanded loss of engine power on one engine and a simultaneous failure of the primary electrical bus, resulting in the loss of multiple flight instruments and the transponder, requires the pilot to implement immediate emergency procedures. Which of the following sequences of actions best reflects the mandated regulatory and professional approach to managing these cascading system failures? Option A. Focus on maintaining visual flight rules, VFR, conditions by looking outside the aircraft and ignore the instrument malfunctions while attempting to restart the failed engine. Option B. Immediately initiate a forced landing procedure without attempting to diagnose or address either the engine or electrical system failures. Option C. Immediately attempt to troubleshoot the electrical system to restore instrument functionality, then address the engine failure. Option D. Declare an emergency, attempt to restore engine power, and then address the electrical system failure and instrument indications according to the aircraft's emergency checklists. The correct answer is C. Immediately attempt to troubleshoot the electrical system to restore instrument functionality, then address the engine failure. Explanation. This scenario presents a professionally challenging situation due to the immediate and compounding nature of multiple system failures during a critical phase of flight. The pilot must rapidly assess the situation, prioritize actions, and make critical decisions under significant stress, all while adhering to strict regulatory requirements for safety. The challenge lies in the need for immediate, decisive action, without compromising the safety of the aircraft and its occupants, demanding a deep understanding of emergency procedures and aircraft systems. The correct approach involves a systematic and prioritized response to the engine and electrical system malfunctions, focusing on maintaining aircraft control, and then addressing the secondary issues. This aligns with the fundamental principles of aviation safety and regulatory mandates. Specifically, the pilot must first stabilize the aircraft by addressing the engine failure, which directly impacts controllability and performance. Following this, the immediate concern becomes the electrical system failure, as it underpins the functionality of essential flight instruments, communication, and navigation systems. Adherence to the aircraft's specific emergency checklists for engine failure and electrical system failure is paramount. These checklists are developed based on extensive testing and analysis to ensure the most effective and safest sequence of actions. The regulatory framework, such as the Federal Aviation Regulations, FAR, in the U.S., mandates that pilots operate aircraft in a manner that ensures safety, which includes the proper execution of emergency procedures. The ethical responsibility of a pilot is to protect the lives of passengers and crew, which is best achieved by following established, proven procedures. An incorrect approach would be to attempt to troubleshoot the electrical system before addressing the engine failure. This is a regulatory and ethical failure because the loss of an engine significantly impacts aircraft performance and controllability, potentially leading to a loss of control if not managed immediately. Prioritizing a secondary system failure over a primary flight control issue directly contravenes the principle of maintaining aircraft control, a core tenet of all aviation regulations. Furthermore, attempting to troubleshoot without first stabilizing the aircraft's primary flight condition could exacerbate the situation, leading to a more severe outcome. Another incorrect approach would be to ignore the instrument malfunctions and attempt to continue the flight as if the aircraft were operating normally. This is a critical regulatory and ethical failure. Instrument malfunctions, especially when coupled with engine and electrical issues, can lead to spatial disorientation and incorrect situational awareness, significantly increasing the risk of an accident. Regulations require pilots to maintain a level of situational awareness that allows for safe operation, and relying on faulty instruments compromises this requirement. The ethical obligation to ensure passenger safety is violated by continuing flight without accurate information about the aircraft's state and its environment. The professional decision-making process for similar situations should involve a clear hierarchy of priorities: aviate, navigate, communicate. First, the pilot must aviate, maintain control of the aircraft. This means addressing the engine failure immediately to ensure stable flight. Second, navigate, determine the aircraft's position and intended course, which in this scenario is complicated by instrument and electrical failures, but the immediate priority is still maintaining control. Third, communicate, inform air traffic control of the situation. In this scenario, the pilot must also consult and execute the relevant emergency checklists for each system failure in the order dictated by their impact on aircraft control and safety. This structured approach, grounded in regulatory requirements and ethical responsibilities, ensures that the most critical issues are addressed first, maximizing the chances of a safe resolution. Question 18. The evaluation methodology shows that during cruise flight, a commercial pilot operating a single-engine reciprocating aircraft notices a significant fluctuation in the oil pressure gauge, accompanied by a gradual increase in oil temperature. The pilot has not encountered this specific combination of indications before. What is the most professionally responsible course of action to take immediately? Option A. Continue the flight as normal, assuming the gauges are temporarily malfunctioning, and monitor the situation from a distance. Option B. Consult the aircraft flight manual AFM or pilot's operating handbook PO for the specific procedures related to abnormal oil pressure and temperature indications and follow them diligently. Option C. Attempt to troubleshoot the issue by cycling the engine's mixture and throttle settings to see if the indications stabilize. Option D. Immediately reduce engine power to idle and initiate a forced landing in the nearest suitable field. The correct answer is A. Continue the flight as normal, assuming the gauges are temporarily malfunctioning, and monitor the situation from a distance. Explanation. This scenario presents a professional challenge due to the critical nature of maintaining aircraft systems' integrity during flight, especially when faced with unexpected indications. The pilot must exercise sound judgment, prioritizing safety and regulatory compliance over expediency. The challenge lies in accurately diagnosing the issue, understanding the implications of system malfunctions, and implementing the correct corrective actions within the operational limitations and regulatory framework. The correct approach involves a systematic and informed response to the engine instrument indications. This means recognizing that a fluctuating oil pressure reading, especially when accompanied by a rising oil temperature, is a serious anomaly that could indicate a significant internal engine problem. The pilot must consult the aircraft flight manual AFM or pilot's operating handbook PO for specific guidance on abnormal engine indications. This document provides the definitive procedures for handling such situations, including recommended actions and limitations. Adhering to these procedures ensures that the pilot operates within the aircraft's design parameters and regulatory requirements for safe flight. The regulatory framework, such as the Federal Aviation Regulations, FAR in the U.S., mandates that pilots operate aircraft in a manner that ensures safety and that they are proficient in handling abnormal situations. Specifically, FAR 91.13 requires that no person may act as pilot in command of an aircraft if they are not competent to do so. This competence includes understanding and responding to aircraft system malfunctions as outlined in the aircraft's documentation. An incorrect approach would be to ignore the indications or to assume they are minor glitches without proper investigation. This is professionally unacceptable because it disregards potential safety hazards. Ignoring a fluctuating oil pressure and rising oil temperature could lead to catastrophic engine failure in flight, posing a severe risk to the aircraft and its occupants. This directly violates the fundamental principle of ensuring the safe operation of the aircraft. Another incorrect approach would be to attempt a fix without consulting the AFM/POH or without a clear understanding of the system. This could exacerbate the problem or lead to further system damage. Such actions would be contrary to the pilot's responsibility to operate the aircraft according to its approved procedures and would demonstrate a lack of professional judgment and adherence to regulatory standards. Furthermore, continuing a flight with a known, unaddressed engine issue that could lead to failure is a direct contravention of the pilot's duty of care and the overarching regulatory requirement to maintain the aircraft in an airworthy condition. The professional decision-making process in such a situation should involve 1. Immediate recognition and assessment of the abnormal indication. 2. Consulting the AFM/POH for specific emergency and abnormal procedures related to the observed indication. 3. Executing the recommended procedures precisely. 4. If the situation cannot be resolved or is deemed unsafe to continue, initiating appropriate actions such as diverting to the nearest suitable airport. 5. Communicating the situation to air traffic control and any relevant maintenance personnel. This systematic approach ensures that decisions are based on established procedures, regulatory requirements, and a thorough understanding of the aircraft systems, thereby prioritizing safety above all else. Question 19. Benchmark analysis indicates that a commercial pilot is faced with a situation where prevailing winds have shifted unfavorably and density altitude has increased since the initial flight plan was filed. The aircraft is operating at near its maximum takeoff weight. The pilot is considering proceeding with the takeoff, believing that the aircraft has historically performed adequately under similar, though not identical, conditions and that delaying the flight would cause significant disruption to the airline's schedule. Which approach to this situation is most aligned with professional pilot responsibilities and regulatory requirements? Option A. Proceed with the takeoff, relying on past experience and a general understanding of the aircraft's capabilities, assuming it can handle the current conditions without a detailed recalculation. Option B. Conduct a thorough reevaluation of takeoff performance using the current wind and density altitude data, consulting the aircraft's performance charts to confirm adequate runway length and climb gradient, and delay the takeoff if the data indicates insufficient safety margins. Option C. Attempt to reduce the aircraft's weight by offloading non-essential cargo or passengers to improve takeoff performance, even if it means a significant delay and logistical challenges. Option D. Make a subjective assessment of the runway length and wind conditions, proceeding with the takeoff if the pilot feels confident in the aircraft's ability to perform. The correct answer is B. Conduct a thorough reevaluation of takeoff performance using the current wind and density altitude data, consulting the aircraft's performance charts to confirm adequate runway length and climb gradient, and delay the takeoff if the data indicates insufficient safety margins. Explanation. Scenario analysis. This scenario presents a professional challenge where a pilot must balance operational efficiency with safety and regulatory compliance. The pressure to maintain a schedule, especially when facing potential delays due to weather or aircraft performance limitations, can lead to compromised decision-making. The pilot's responsibility extends beyond simply flying the aircraft. It includes a thorough understanding and application of performance data, weight and balance principles, and the associated regulatory requirements to ensure safe operation under all conditions. The ethical dilemma arises from the potential conflict between meeting operational demands and adhering strictly to safety margins dictated by regulations and performance limitations. Correct approach analysis. The correct approach involves a meticulous review of all available performance data, including takeoff and landing charts, considering the prevailing environmental conditions, density altitude, temperature, wind, and the aircraft's current weight and balance. This includes a conservative assessment of runway length requirements and climb performance to ensure adequate safety margins are maintained. The pilot must then make a decision based on whether the aircraft can safely operate within the established parameters, even if it means delaying the flight or diverting. This approach is ethically sound and legally mandated by regulations that prioritize safety above all else. Specifically, regulations governing commercial pilot operations, e.g., FAA Part 121 or equivalent, require pilots to ensure that aircraft performance is adequate for the intended operation, taking into account all environmental factors and aircraft limitations. This includes a duty to refuse to operate if conditions are unsafe. Incorrect approaches analysis, an approach that prioritizes departing on schedule without a thorough reevaluation of performance data, assuming the aircraft will perform adequately based on previous experience or a cursory glance at charts, is professionally unacceptable. This fails to account for the cumulative effects of changing environmental conditions and weight, potentially leading to a situation where the aircraft lacks sufficient takeoff performance or climb capability, creating a direct safety hazard. This violates the pilot's fundamental duty to ensure the aircraft is operated safely and within its performance envelope. Another incorrect approach would be to make a subjective judgment about runway length or climb gradient based on a feeling or a quick mental estimation, rather than consulting the specific charts and data for the current conditions. This bypasses the established, data-driven safety procedures and introduces an unacceptable level of risk. It is a failure to adhere to the regulatory framework that mandates the use of specific performance data for operational decisions. Finally, an approach that involves attempting to push the aircraft's performance limits by, for example, accepting a reduced safety margin on landing distance or assuming a higher than actual climb gradient, is also professionally unacceptable. This demonstrates a disregard for the established safety factors built into performance calculations and a failure to uphold the pilot's responsibility to operate the aircraft within its certified limits. This directly contravenes the spirit and letter of regulations designed to prevent accidents caused by performance exceedances. Professional reasoning. Professionals in this field should employ a systematic decision-making process that begins with a comprehensive understanding of the operational context and regulatory requirements. This involves 1. Proactive data gathering, obtaining all relevant weather, performance, and weight and balance information. 2. Objective analysis, rigorously applying the data to the aircraft's performance charts and limitations. 3. Risk assessment, evaluating the potential consequences of any deviations from optimal performance. 4. Decision-making, making a clear, safety-first decision based on the analysis, even if it impacts schedule. 5. Communication, clearly communicating the decision and its rationale to all relevant parties. This structured approach ensures that decisions are grounded in fact and regulatory compliance, minimizing the influence of external pressures and subjective judgment. Question 20. The review process indicates that during a pre-flight briefing for a cross-country flight, a commercial pilot reviewed the METR for the destination airport, which showed clear skies and light winds. However, the pilot noted a TAF indicating a significant probability of severe thunderstorms developing along the route of flight within the next few hours, accompanied by moderate to severe turbulence and hail. The pilot also observed a convective signet for the general area. The pilot is concerned about arriving at the destination on time for a scheduled passenger pickup. What is the most professionally responsible course of action for the pilot? Option A. Delay the flight until the convective signet has expired and the TAF indicates a lower probability of severe weather. Option B. Proceed with the flight as planned, assuming the thunderstorms will be avoidable and the turbulence will be manageable, given the clear conditions at the destination. Option C. Depart as scheduled and rely on onboard weather radar to navigate around any developing thunderstorms. Option D. Obtain a more detailed weather briefing from Flight Service Station, FSS, and discuss potential routing options to avoid the forecasted thunderstorm activity. The correct answer is B. Proceed with the flight as planned, assuming the thunderstorms will be avoidable and the turbulence will be manageable, given the clear conditions at the destination. Explanation. This scenario presents a professional challenge rooted in the pilot's responsibility to maintain situational awareness regarding weather and to make sound decisions based on that information, even when under pressure. The ethical dilemma arises from balancing the desire to complete a flight with the paramount duty to ensure the safety of the aircraft, passengers, and crew. A pilot must always prioritize safety over schedule or personal convenience. The correct approach involves a thorough review of all available weather information, including forecasts and current reports, and making a conservative decision based on the potential hazards identified. This aligns with the fundamental principles of aviation safety and regulatory requirements that mandate pilots to be proficient in weather interpretation and to avoid hazardous conditions. Specifically, Federal Aviation Regulations, FAR, require pilots to obtain and review weather information before flight and to discontinue a flight if hazardous weather is encountered or anticipated. The pilot's ethical obligation is to act as a prudent aviator, which includes acknowledging limitations and making decisions that err on the side of caution when faced with uncertainty or significant weather threats. An incorrect approach would be to dismiss or downplay the significance of the reported severe thunderstorms and associated turbulence, perhaps due to a desire to avoid delaying the flight or due to overconfidence in personal flying skills. This demonstrates a failure to adhere to regulatory requirements for pre-flight weather briefing and a disregard for the inherent dangers of thunderstorms, such as severe turbulence, lightning, hail, and microbursts. Ethically, this approach prioritizes expediency over safety, which is a direct violation of the pilot's duty of care. Another incorrect approach would be to rely solely on a single, potentially outdated weather source or to make a decision based on incomplete information. For instance, only checking a METR without considering the TAF or PIRP for the intended route and destination would be insufficient. This reflects a lack of diligence in the weather briefing process and a failure to synthesize all available data, which is a critical component of safe flight planning. The regulatory framework emphasizes a comprehensive understanding of weather conditions. A third incorrect approach would be to proceed with the flight with the hope that the weather will improve or that the hazardous conditions will be avoidable en route, without a concrete plan or sufficient information to support this assumption. This is a form of wishful thinking rather than a professional risk assessment. It ignores the unpredictable nature of severe weather and the potential for rapid deterioration, leading to a situation where the pilot might be forced to make critical decisions under extreme duress, potentially compromising safety. The professional decision-making process for similar situations should involve a systematic approach. 1. Comprehensive pre-flight weather briefing. Obtain and thoroughly review all relevant weather reports and forecasts, METR, TAF, PIRP, AIRMET, SIGMET, surface analysis, prognostic charts from multiple reliable sources. 2. Hazard identification and risk assessment. Identify specific weather hazards, thunderstorms, icing, turbulence, low visibility along the proposed route and at the destination. Assess the potential severity and likelihood of encountering these hazards. 3. Decision-making. Based on the risk assessment, make a go/no-go decision. If the risks are unacceptable, consider delaying the flight, altering the route, or canceling the flight. 4. Contingency planning. If proceeding, develop contingency plans for encountering unexpected weather or for diverting to an alternate airport. 5. Continuous monitoring. During the flight, continuously monitor weather updates and be prepared to adjust the flight plan or take evasive action as necessary. 6. Conservative judgment. When in doubt, err on the side of caution. The safety of the flight is always the highest priority.